Let's look more at K. We'll practice writing some K expressions, figure out what we do when we have a bunch of different stuff in the system. What if we have something that's aqueous and something that's liquid? What if we have a solid? All right, let's take a look at that. And then let's explore just a little bit to start with what the size of K means. All right, let's take a look at these K expressions. So we're looking at a constant ratio. All right, so everything is going to get to that ratio. And when we have Le Chatelier's principle, we perturb the system, and the system will adjust to get back to that ratio. And so we have that equilibrium constant. All right, so K is going to equal those reactants over the product. Those products over the reactants. Saying it backwards as I'm staring at something. It's products over reactants. And we raise each thing to whatever coefficient is in front of it. All right. So my products here, I have product C with coefficient C. I have product D with coefficient D. I have reactant B with coefficient B, reactant A with coefficient A. All right. And so we just write it with those coefficients raised, and it's those those products over the reactants. I don't know why I'm saying it backwards. Products over reactants. Okay, now I've seen just the generic equilibrium constant be written as K, Kc, or Keq. All right, those all mean the exact same thing. Though we do sometimes use some other subscripts on our Ks just so we have an idea of the type of system that we are considering. All right, and so let's say we have a bunch of gases and we care about pressure instead of concentration. All right, we might see a K sub P. So what we're looking at here is pressure. All right. All the rest of the Ks are done in terms of concentration. And when I talk concentration, I've been using these square brackets, right? All right, remember those square brackets means concentration of the species in molarity. Okay, so those square brackets mean the concentration of the species in molarity. And so pressure, the Kp, that's a little bit different because we're considering pressures. So we would use atmospheres or torr. Everything else we're dealing with is in concentrations of molarity. Okay, and so again, just our generic K, Kc. All right, so anything. This could be any system. And this is concentration only, okay? So again, Kp is the only pressure. Now the rest of the specific Ks that we look at, again, will also be concentration. And so when I'm thinking about acids and bases, I can get a Ka or a Kb. All right, and so our Ka is our acid dissociation, and Kb is our base dissociation. All right, Kw, which you should have learned in your prep class. This is that auto-ionization of water. So when water is in equilibrium with itself. And then Ksp is what we call the solubility product. And that looks at substances that are either very slightly soluble or considered to be insoluble, just how much might actually dissolve. All right, and so they all go back to this, okay? Everything goes back to K or Keq. But when we put those subscripts there, it lets us know immediately the type of system we're looking at. Okay, so let's look at a couple of these. All right, so I said Ka was an acid dissociation. So here is an acid. And so these are for weak acids. All right, there's only a few strong acids, which you should have memorized. There's only a few strong acids. Every other acid is a weak acid. And so what you've learned, hopefully you remember this, is that weak acids only dissociate slightly, okay? And so something like hydrocyanic acid, we're going to put it in some water, and it'll dissociate into our hydrogen ions, and since water's present, it'll make H3O+, the hydronium ion. And that's cyanate anion. And so our Ka, we're going to take the hydronium ion, and that's cyanate over, okay? Likewise, most bases are weak, right? There's only a few strong bases. And so I can look at a weak base like ammonia, and I can write the same sort of equilibria. We're going to put it in some water. We're going to get some ammonium ions and some hydroxide ions. Okay? And so our Kb will look like this. Okay? Kw, I'll refresh you on, but you should have learned this one in your prep class. If you took Chem 120 at Grossmont, you should have learned this. And so we've got water in equilibrium with itself, because remember, water can act as both an acid and a base. And so we can get this, where I get hydronium and hydroxide. What am I doing? I'm already thinking ahead to writing the Kw expression. Sorry about that. Okay, and so my Kw. So hopefully this looks familiar. And if you remember, this is a 1.0 times 10 to the negative 14th. Hopefully that seems familiar. Okay, and then there's that KSP. All right, so something like calcium hydroxide. Okay, and so our KSP, we're going to take that calcium ion. And we have 2 of those, okay? Now notice the pure liquids, like liquid water, and the solids don't show up, okay, when we write these expressions. Okay, so now, to start off with, for you to practice, I'm going to show you some reactions where everything is in the same state, and everything will show up in the K expression. All right, so I want you to take a look at these. So based on how I have written some of these K expressions so far, I would like you to write K expressions for these 4. I want you to try them before you see my solution. So pause the video, give these a shot, and then unpause. Remember, we're looking at the products over the reactants. Okay, and in these, everything shows up. So pause, try them yourself. All right, well, hopefully you followed my instructions and tried them yourself. So let's see how you did. So our first one is going to look like this. Okay. Our second one Okay, and the third one. And lastly, the fourth one. All right. So remember, just products over reactants and then raise anything to a coefficient. Okay. All right, now, when we do have heterogeneous systems, so the last ones were all homogeneous, everything was the same. When we do have something that's heterogeneous, okay, so I've got a reaction going here where I've got, let's see here, I'll take some room up here. I've got 2 carbon monoxide decomposing to carbon dioxide and solid carbon. Okay, so pure solids and liquids don't change in concentration, so they're not included in the K expression. Okay, so not. All right, not included in that K expression. Okay, and so for this one, K would be just that carbon dioxide over the carbon monoxide raised to that second power. Okay? Okay, so here's some for you. Pay attention to what the states of everything are and see if you can write these K expressions. Okay, again, try them with it on pause and then unpause and see how you did. All right, hopefully you followed my instructions. All right, our first one, our mercury 2 oxide was a solid and mercury was a liquid, so the only thing that's going to show up in our first one is the oxygen. Okay. For our second one, everything was gaseous, so everything's going to show up. Okay, our third one, we had some solid carbon. Now our third one was just that last reaction from the previous slide inverted, okay? And so we're gonna get, this time the carbon monoxide's on the top, raised to the second power over that carbon dioxide. All right, and the last one, both of the reactants don't show up because one is a solid, one's a liquid, and so we're only going to get those products. So we're going to get hydrochloric, well actually it's a gas, so it's hydrogen chloride gas. All right, and it looks like that. Now, what if you had a situation where you had, some reactant that was aqueous plus another reactant that was aqueous, and then your products were something like a solid. Okay. What if it was something like that? What happens if you have a situation where your product doesn't show up? Because products go on top. So think about that for a second. What can you do? Well, it would be like this. Because I don't put the product in there, I'm going to put 1 over. Like that. Okay? All right. And And so when we look at K, most things as I perturb my system aren't going to affect the value of K. So if I increase or decrease any component, all that's going to happen is my system's going to shift for that particular component, and it's not going to change K. If I mess with the pressure or the volume, where I have gases, still not going to affect K. All it's going to happen is I'm just going to shift to adjust for my system. But if I mess with the temperature, that's going to depend on if I have an exothermic or an endothermic system. All right, so not only does the system shift, but the value of K can change as well. And we'll look at that more toward the end. And then a catalyst, if you don't remember what a catalyst is, you did use one in Chem 120 if you took it at Grossmont, but a catalyst just makes something, makes a reaction easier to do. It basically lowers the activation energy. So let's say something needs to be at this much energy for a reaction to occur, but with the catalyst it only needs this much energy for the reaction to occur. That means the reaction will go faster, and so catalysts are often used to get it to go faster, but we still reach that same equilibrium constant. Okay, now that we understand what the equilibrium constant is and how to write those expressions, we're going to start doing some numerical work. All right, calculations coming up.